welcome to our first hybrid SAMS webinar, which is joined with the NSF AI Physics Planning Institute at Carnegie Mellon. It's a pleasure to introduce Dr. Kaze Wong, who's a research fellow at the Flatiron Institute, studies black holes through gravitational waves. Kaze graduated from the Physics and Astronomy department at Johns Hopkins University, and he's also a recipient of the 2021 GWIC Braccini Prize for his thesis work on building new tools for gravitational wave astronomy. Kaze's research centers around the intersection between physical sciences and deep learning, and he's particularly interested in building production-grade hybrid methods to take on challenges in physical science. So please.
Okay, so this is all this thing. Okay, should we good? Some people see myself good. I also need to click it here. So hello everyone, I'm Kaze. I work on gravitational wave. I study black holes. That's half of my job, and the other half of it is like figuring out what deep learning, machine learning techniques we can use to enhance the analysis or simulation tool that we've been using to study gravitational wave and black holes. And also, recently broadening to study not just gravitational wave, things like protein structure, exoplanet, quantum images. Those I usually, I don't look at them extensively. I'm tapping into that so we can see whether the method is actually general to be applied to a broad class of problem instead of just gravitational wave. So I whipped this up in a couple of days. So there's always these hassle that you're trying to figure out. Is this a lot of material? Is it not enough material? So I try to lean on the less material side, and I've been told that this is more like a colloquium to just speak. But if you have questions that you want to drop by, a quick question, feel free to do that. I'll be more than happy to have this as a more interactive thing over time. Because 45 minutes is pretty long. People will get sleepy. That's understandable. But yeah, so because this is a broad audience, I assume not everyone knows exactly what gravitational wave is and what the thing that I'm trying to study. So the first part would just be talking about briefly what the idea of gravitational what they are. So what's the story so far? Why this is not working? There you go. So what's the story so far? What's gravitational wave? So in 1995, there's this young dude that figured out a theory that to describe gravity. So he, instead of like making gravity a force that one sent to another and to do this force, he think geometrical description fit gravity better. As in, if you put Earth in the middle, you can actually just curve the space-times around it. And if you have a beat that you roll down the fabrics around it, it will go around the Earth. That's how the Earth, attracts us. And also the reason why Earth go around the sun is just curved space-time. There's no such thing as magical force called gravity. It's just curvature of space-time that's doing its thing. So one of the prediction that Einstein general relativity theory predict that is confirmed in 2015. There should be an audio, but I was informed that the audio doesn't work. There's like a blip sound that you should be hearing. But these are the first detection, direct evidence of gravitational wave. I'm going to play it again. Okay. So the x-axis is time, and this is a spectrogram. On the y-axis is the frequency, and you see the two signal. They kind of went by, these are the gravitational wave signal that comes in. If you can hear the audio, it will be like a chirp, like whoop, that kind of stuff. That's the first direct evidence of gravitational wave I've seen. Timely, 100 years after Einstein theory prediction. And this signal, we think, given the theory of general relativity, we think these signal, these wiggle that we see in our data, and again, like x-axis is time, y-axis is some relative change in the length of some ruler that we put down, is sourced from a pair of black holes colliding in spiraling and merging very far away from each other. I mean, very far away from us. And the gravitational wave emitted by these pair of black hole colliding get to Earth, change something in our detector, and we've seen them the first time. So that's the idea. The universe is space-time in a sense, and there's these two black holes very far away collide, and then this gravitational wave at some point passed through Earth in 2015, and we detected them. That's the idea of space-time. The ripple, gravitational wave, the ripple of space-time. So that was cool in 2015, and the years follows, we detect many other exotic things to us, at least. In 2017, we saw the first pair of neutron star binary, and this time not just gravitational wave from it, but also electromagnetic wave like light, X-ray, gamma ray, radio ray, they all come together. So this was a very interesting event because it's one of the first few for like multi-messenger, like as in you have gravitational wave and lights together from the same event that we're seeing. And there's also other exotic things that we've seen. And this is an event that we detected in 2019 that give us kind of some direct evidence to some black hole that is at that mass. So it's getting into the intermediate mass range black hole. We kind of know there exists. We have a lot of indirect evidence, but like after this event, we kind of know, oh, they're actually black holes that is around 100 something solar mass. We have indirect evidence for them for a long time, but that was, I think, the very first, direct evidence of black hole of this mass. This is the remnant. You have two black hole. You have two black hole merged into 150 solar mass remnant. So that was some cool story. And so where we stand today. So we've been detecting this ripple of space-time for about 7 years now. It was surprisingly long ago to me. It feels so old when I talk about 2015. And this is where we stand today. There are already 3 observational runs that we keep upgrading our detector and turning them back on. And this is where we stand currently. All these blue points, I should use the cursor to gesture. All these blue points are the black hole pair that we've detected through gravitational wave observation. And the orange point here are binary neutron stars that we detect through gravitational wave. And there are a number of other observations. These are usually in isolate through electromagnetic wave, like neutron star telescope, stuff like that. And the thing that we detect through gravitational wave usually are binary, because only binary generate enough gravitational wave for us to detect. And this picture looks empty before 2015, and it's actually surprising. In 7 years, to reach to us, to the gravitational wave community, it's surprising that, well, not all that surprising, but it's also good to see we have this amount of data that we have now. Because 7 years ago, nobody dreamed of this. People are still waiting the first detection of gravitational wave. We don't know whether it exists, but today it's like a common thing. When I was in my PhD, I was scolded by my supervisor that this guy doesn't know anything about being grateful for detection, because he's been working on that for 20 years. And I was like, oh, there's another data detection. Great, let's go for lunch. And he's like, why are you not excited? So I see that like 5 times now. Well, it's not exciting to me. But yeah, so it's getting a little bit more, common and common. And it's surprising. What I'm trying to say is it's surprising to the community how far we've come in just 7 years. Now, this picture to the gravitational wave community seems like a lot of data. We've seen a lot of different things so far, but if you do a little bit counting, this is around 90 or 80 even, and we're trying to do statistics, right? Like with 80 or 90 points. So if you come from a more traditional astronomy background or some other background, imagine that the moment that you start to do statistics, you at least go around the street and collect a couple hundred surveys. And this is not that. This is like, half your survey. So that's kind of why we come up with the title, Data Scientists on Diet. In gravitational wave, there is seemingly not a lot of data. I'll get to that a little bit more. But before we go into that, let's talk about in the future how gravitational wave is going to look like. So people have been thinking about different upgrades to gravitational wave detector. We always want bigger thing. like more exotic thing to go after the next target, right? Otherwise, we go out of job. We don't have next thing to study, right? So people are thinking next generation detectors like Einstein telescope in Europe, Cosmic Explorer. It's a US-based effort trying to scale up the current facility. They need to find a new site and all that. And there are project that is funded. I think it's in ESA phase B or something. Maybe they just passed phase A, some engineering phase. That LISA, it's going to be a space-based gravitational wave detector that we're going to launch in space and trail Earth and detect another class of class of gravitational wave signals. So what these detector can do, of course, when you upgrade them, they bring a couple perks, right? So for the ground-based detector, this is a figure that like made by the community, one professor from MIT. Is a simulation to show what the capability of ground-based detector is. So the dots are some simulated event that we think we'll see. I mean, the universe is producing constantly. The lines here are kind of like different, the horizon of different detector. So LIGO, LIGO is not even here, I think. LIGO is like much closer. But you can see the next generation detector, like CE2, ET, all these things, they're out here. What does that mean? That means anything, after we view those detectors, anything in the universe that is like a binary neutron star black hole, if they merge, we'll see them up to redshift 100 or a couple hundred. So practically everything that in the universe. That's why the name like Einstein, Cosmic Explorer. Just in the right mass range, anything that merged in the universe, we'll see them. We'll see complete universe. Well, that's cool to me. I don't know. And we'll see a lot of them. And the number of events per year that people are thinking of, like these detector will detect, is about 10 to the 6. So now I'm having 90 events and I'm yawning at the new event. Imagine when we have 10 to the 6 events per year. So that's a lot of events in the future. Then another thing that promised by the next generation detector are like the space. So why do we want to go to space? If we want to detect lower frequency or another type of gravitational wave, they usually live in like lower frequency range, which means they correspond to a longer time scale, and longer length scale. And the current arm length of gravitational wave detector is about kilometer scale. Okay, and when we scale up the ground base, we can scale up to like 40 kilometers. But to detect these millihertz gravitational wave signal, you need a couple tens of thousands kilometers arm length to do that. So good luck finding that on Earth. We're not doing that on Earth. We're going to shoot that into space. And what LISA will promise us is supermassive black hole. So instead of black hole that is a couple tens of solar mass, LISA, this space-based facility, they will find black hole that are 10 to the 6 solar mass. So these will be galaxy merger or some other thing. Okay, so drastically different. Like ground-based detector, they're gonna detect many more events. Space-based detector, they're gonna open up a new window to completely different events. Okay, that's the future that we're kind of looking into as a gravitational wave community. Now, it's a good thing that we have new instrument, and it's a good thing that we have more exotic target to chase after. That's a blessing, but that comes with a curse as well. And I'll get to more precisely what do we mean by a curse later. So this is on the x-axis is the number of days of observation. It's kind of like uptime of our detector. On the y-axis is the cumulative number of detection. So the different O1, O2, O3A, O3B are the different observational run. In between them, we kind of upgrade our detector. Gives our instrumentals a break, and then they come back and find us more events. So you see, at O2 to O3A, we upgrade the sensitivity of our detector by around factor 2, I think. But like the rate of detection, because it's a volume, so it's like 2 to the cube, so it increased a lot. Most of the event that we've seen comes from O3, and this every time we upgrade, this curve is going to keep doing this exponential geometric growth. So this is the kind of the prediction that actually my office made during his PhD. My PhD as well, that he made a prediction of how the number of detection will grow over the year. So on the x-axis, let me get darker. On the x-axis is the is the year prediction. Unfortunately, we are hit by COVID, so a couple of years setback. But the size of the gravitational wave catalog, you can see this is log scale. So I mean, this is like still a decade ahead. But at some point in the future, probably in the 30s, like 2030s, we're gonna reach 10 to the 5, 10 to the 6, or even 10 to the 6 event. So this is a lot of events to handle. That means that we have a lot of work to do. Good. The curse part comes in something that I'm gonna tell you in the second part of the talk. But like to be brief, analyzing 10 to the 6 event is not easy. We are taking half a year to process the event that we have in O3A and O3B. So like from finished data taking to releasing the catalog paper and all that takes about half a year to a year for 90 events. Well, I mean, good luck with 10 to the 6 event. I don't know how many more years we'll need to release the catalog of that size.
So why does it take so long? Does it scale with the number of events?
I'll come back. It has political effects, but also there's a very practical problem that I'm going to get into. Okay. But also, as we upgrade the detector, our sensitivity increase, and what that means we can look into more like smaller systematic, which means we put a more stringent accuracy requirement to our theoretical model. So that's a curse to like the theorists, like, okay, give me a more accurate number, otherwise, we'll dominate by the systematic in our model, things like that. Okay, so that's like a whirlwind description of how gravitational wave, the landscape challenges, where we stand now. Now I'm gonna like talk about why gravitational wave seems to be harsh to data scientists. Well, when I say data scientists, I'm not saying in general the whole world no one can tackle this problem. It's like people who have devoted their effort into looking at this seems to not have the proportional success as compared to the DeepMind or the industry. Okay, so people that try to take off the shelf or not so off the shelf, they try to do something that is not entirely expert in deep learning, trying to use this method in gravitational wave, and it seems to not work very well. And there's a couple reasons to that. First, gravitational wave measurements are extremely noisy. So on the x-axis, this is a time series that like what you will see in a gravitational, well, not exactly, but some cartoon version of that. But this is a cartoon version of what you will see in a gravitational wave detector. On the y-axis is kind of like, again, strain. So what you would like the signal. The blue line, the deep blue, it's what the actual signal that you read out of the detector look like. And the underlying signal that we put in, like, we kind of put in by hand, like physically, this again, a cartoon, is in the cyan line. So if I don't show you the cyan line and I tell you there is a signal inside, not entirely trivial to me where exactly the signal lives, right? It's not like you can pick up by eye, this is the peak, because it's not, right? So it's extremely noisy measurement. So with off-the-shelf algorithm, people seem to struggle to figure out how to pick out these very small signal in your very noisy data. And this noisiness can also be reflected on some of the results on solving inverse problem in gravitational wave. So on the x-axis, this is parameters that we think the first event has. So x-axis, the primary mass, the heavier mass in the binary. Second, the y-axis, the secondary mass, the lighter mass in the binary. And mass is actually the thing that we measure the best in gravitational wave. But you can see how uncertain we are about the mass of the gravitational wave source, right? The mass, like when people say, oh, LIGO detected a 30-30 solar mass binary. What do they really mean is like somewhere from 30 to 40. We don't know where exactly the mass is. It's pretty noisy. And given how noisy our data is, we still can make statements like this. I think it's pretty remarkable. But the first point is, gravitational wave, pretty noisy data. It's not something as trivial as like, oh, there's a dot there. Let's run the CNN on it, find the dot, sort it, right? It's not that. There's a little bit more work that you need to do. Second, we actually need to extract that noisy data. What you need is a very accurate model. And without a very accurate model, I'll explain what this figure means. Without a very accurate model, you just cannot coherently add the signal enough to detect that. So on the x-axis, it's kind of network SNR. What is a network SNR? is like if you have a network of detector, you can combine the data in a meaningful way that will give a signal to noise to a particular event. And as you upgrade the detector network, you get better and better NZR for specific events. Okay, so the same event, because you upgrade your detector, the signal to noise ratio is going to go up. Good. On the y-axis is kind of measuring the error in a different component of a modeling process. So there are different modeling processes. There are calibration in the detector. There are errors from our numerical relativity simulation. These are simulations of black hole, just down to direct integration of that. And there are parts that take that simulation and turn them into a fast approximation. So every moving part in our analysis pipeline has some error. And the dominant one is, so the y-axis is kind of measuring the error in different components of our pipeline. On the x-axis is kind of our SNR. So currently we are at some point here with HLDK, where we stand now. So the dominant error that we kind of have now, which is still tolerable, at this point is still tolerable, is this semi-analytical model. So we take numerical relativity, approximate them with some approximate, and we're dominated by that. But as we upgrade our detector, even direct integration, the best simulation that you can find on Earth on black hole, they're not accurate enough to capture the data that will be present in our future detector. And at some point, you just run into calibration errors, like we don't know what to do with our detectors and stuff like that. Hopefully, people will push that down. But my point here being, gravitation, and you see the error requirement here drop by 10, 3 or 4 order of magnitude. And through 30 years of engineering, we reached 10 to the negative 2, which is 2015. But going into the future, we'll need higher and higher accuracy. So usually when you're trying to, pull off some scikit-learn, PyTorch, default technology, or you train, it's about percent level, you clap and you pat yourself in the back and say, a percent job is okay. A percent job is not okay here. We need a percent of a percent of a percent, it's your guess.
So what happens if you don't? What do you misestimate physically if you don't get that?
So if our numerical relative, so your instrument is capable to do 10 to the 6. Let's say we can measure the mass down to 10 to the 6 precision, but your model is only accurate 10 to the negative 4. So you can your uncertainty will be dominated by your model uncertainty. It's like we're not really sure what the mass of the.
So you're saying you're dominated by systematics.
Yeah.
But if the systematic error on the mass is 10 to minus 4, I would think. I don't care it's 30 years.
Yeah, there are questions of whether people care, but the thing is, maybe at that point you don't care about the mass, but there's some higher or either for example the spin. Maybe you care about the spin to 10 to the 2, but to measure the spin 10 to the 2, because it's the second order effect, you need to first measure the mass correctly, then you can measure the spin correctly. I mean, it's very handy, but there are higher order terms that you care about that it correlates with the first order term. So if you don't measure the first order term correctly down to a certain level, then your higher order term will be dominated by systematic at that point. Does that make sense?
It makes sense, but it would be interesting to see. Yes.
Yeah. But there are things that quantity that people will be up to. Okay. And finally, there are 3 reasons, usually we're trying to put 3 reasons. And one of the reasons why gravitational wave is hard is just outliers everywhere. So these are the screen cap that I got from the paper release website, that for every outlier, the reason why people are publishing this new event is because they think they're interesting. Okay. So in 2015, there's obviously the first detect. And you can see there is we detect a 22 solar mass black hole, new paper. Okay, surprising. So and then they detect a 50 solar mass black hole at redshift 2, maybe new thing, outlier. And more, as time goes on, we detect saying people. I mean, I'm not saying these are fundamental outliers. I'm saying people treat them as outlier. So there are out of the catalog at the time of 2019. We have around 20 or 30 events or so. We have half of them being, outliers. Outliers in the sense that we don't know what they are. So that's a problem, right? Because if you don't have some very well-defined distribution in whatever you're trying to learn, if everything is outlier, what were you doing? Right? You're just classifying everything as outlier, so you don't really learn much. So at least in the community, that's kind of how it views. So it's kind of hard to just throw some off-the-shelf algorithm to learn something that is just everything is outlier. Okay. So gravitational wave is pretty harsh to the community. People always trying to pull in new deep learning algorithm, get rejected in referee court because like this either be beaten by a traditional method or it just doesn't work. Now, how we? Oh, by the way, I forget I put this in. But these are, if you're trying to search for gravitational wave, and these are all the, well, I mean, not all, but a lot of glitches. So none of these are gravitational wave. The gravitational wave may look something like this, but this one is a terminal wave. So if you just want to throw deep learning algorithm on, learning how to find gravitational wave, more often than not, you find like an air compressor going off, or maybe a bird land on your vacuum tube and poke it, and you find something like extreme loud, I think, and stuff like that. So there's a lot of it's very noisy data. There's a lot of wild things that we can and cannot imagine is going on. So throwing just off the shelf deep learning on it doesn't seem to have a lot of luck. Now, so I kind of think that this is on the data type. We don't have very high quality data. We don't have a lot of data that we can train on. Then what do we do? What do we do when we have? Apparently, we cannot leverage most of the big data advancement in the recent years. So what do we do when we don't have? We cannot leverage off-the-shelf thing. Okay, so the rest of the talk is going to be 2 case study of like what we're going to do. I'm going to break the suspense and just tell you we should use hybrid method. What do I mean by hybrid method? I'm going to go on 2 case studies. Let me just check the time. Okay. And I'm gonna talk about so it's 2 case study. Let me know about the time, so I can go through them more quickly. Why not? Good. So the first thing is something called inverse problem. So we've seen that figure before. On the x-axis again, like strain, and the problem that we're trying to solve here is if you're given a strain, I want you to tell me what is the mass of the underlying event that comes from. And people can kind of solve this problem. Right, I give you a data and you tell me what is the parameters that consistent with this observation given the theory. Okay, so this is an inverse problem. I will gonna get to why is it so expensive, and the way that we solve it is just a good old Bayes theorem. I just talked to some of you, and apparently the whole gravitational wave community is like Bayesian, basically. So it's like kind of refreshing to tell you, oh, have you tried frequentis? Like no, but this is all we talk about when we talk about statistics. We want to know the probability of this parameters being consistent with given some data. So given some data, what is the probability of our event is a certain parameters, like certain mass. That is like just Bayes theorem. You write down your likelihood, that's your model of the noise, your model of the signal that you want. That is the strain model. That is the model of the signal here, which is denoted by H. H is the strain. So given the data, you can write this down. This is just your likelihood, okay, your model. And you always need to set a prior, like mass cannot be negative, okay? I don't think we can argue with that, maybe one day, but not now. So you need to define a prior, evaluate the product, the evidence. We don't need to talk about the evidence now. Like for the moment, let's just because this is just a normalization factor, you don't need to worry about them if you just care about the shape or the distribution of theta. So in principle, you can go into each data extensively, poke them, evaluate your likelihood, evaluate your prior, multiply them together, get a bunch of number, and retain only part of them. Okay, so you can run MCMC and stuff like that. That's fine. And now I'm gonna get to why is it expensive and not working. There are a lot of reasons. So in the catalog that I just showed you, the 90 event that we have costs around 100 million CPU hours to estimate 90 events. There's a lot of reason behind that. Some of them is engineering, some of them are political, but there's a critical bit afterward. If you convert this into CPU hours and you just go on Google and pay that amount, it's about like a couple million. So that's 90 events. And I said this a couple minutes ago that in the future we're gonna have 1 million resources every year. So I don't think we can pay that number. So we have a problem. We need to solve this. Otherwise, we're not getting the science that we want. Good. So now why is slow? We're gonna get to that. Let's talk about MCMC. What is MCMC doing? I love this website. It's called Interactive MCMC Gallery. I encourage everyone to go look at it. It's amazing. I didn't make it, just to be clear. So what you're doing in MCMC, basically, let's say the contour is the target, and you're proposing jump based on where you are, and you're rejecting some of them. So if it's turned green, you accept. If it's red, you reject. And you kind of keep doing this, keep moving around the space. And after you do it for a while, then you're left with a bunch of points that kind of proportionally distributed with your posterior, or your target distribution. Okay, that's kind of MCMC, the idea of MCMC. Now, you kind of only get information out of this when you accept a point, because like if you reject, you stay where you're at, so you don't move. You can imagine if you have algorithm that 100% reject, just staying where you're at. You don't actually explore the space and go with a distribution that you want. So by the virtuous having rejection, like if your target look like this, and you're proposing point in region that is not very relevant, you're kind of being very inefficient. And evaluating each one of these points may take somewhere from 10 milliseconds to a second, some of them take to 10 seconds. So you need to, typically people need to evaluate 10 to the 6, 10 to the 7 likelihood trial to get a converging MCMC run. So that's why it's inefficient, and it takes a lot of time to do. There's an engineering aspect to that. I'm not going to go into that now. But it's
so it's slow. It's fitting for the masses, not seeing if an event is a signal.
Yeah, like detecting it is fine, but we don't actually do this for in 2 dimensions. We do it in 15 dimensions. So in 2 dimensions, you already have like some volume factors that you're living here. Imagine you're living in a 15-dimensional space. So you're just very unlikely, unless you be very smart, to propose in a region that you accept. So that's why.
Is this with a single template, or is this sampling over a bunch of them?
This is sampling. Every point that you see here is like a different template. So from one template you propose another new parameters and you use that template.
And can you neglect the denominator, or do you have to do the evidence?
The denominator don't. Well, in just estimating, the denominator is normalization factor. So like the value here, if you just multiply by normalization factor, it doesn't matter. Distribution doesn't change.
So you don't have to use that to discriminate amongst the templates.
Yeah,
their parameters.
Yeah, we don't do that. I mean, we do that, but like for another context, another problem, which is not relevant. So that's why it's slow. And people have been proposing like different methods to solve this. Instead of doing MCMC, can we do something else? So there's something called normalizing flow. I don't know where, like some of you are familiar with, some of you are not. But this is an animation that I made a while ago to explain the idea of normalizing flow, and I'm proud. So I'm going to show you that. So the idea of normalizing flow is, if you start with, let me pause this for a second. So everyone know how to sample a Gaussian. Everyone know how to like write down a Gaussian and a multivariate Gaussian. And now if I have a parameterized transform, so it has to satisfy some properties, like it has to be bijective, you have to easy compute Jacobian and stuff like that. But you can write down a parameterized transform, which you can tune parameters. Then you can transform this, so like these white dot down there is like kind of some synthetic data that we generate just to illustrate the idea. So what you can do with a Gaussian and a parameterized transform is to tune the parameters and wrap the Gaussian around. And as you do that, you wrap the Gaussian to look like your data. And then because you know the mapping, you finish tuning it, you can go back and forth between your prior space, which is the Gaussian, which you know how to sample, you know how to evaluate the probability. And then you take that, like imagine if you want to sample, you just sample from the Gaussian, push forward through the parameterized transform into the new space. Okay, so that's the idea of normalizing. Normalizing is like write down a Gaussian, have a bunch of parameterized transform, tune the parameterized transform until it matches the data, and voila, you can have the PDF of a particular distribution of points. So people try to do that with gravitational. So instead of sampling and evaluating the likelihood, so previously, I actually reversed the order. Okay, so previously we were evaluating whatever here. So for every theta, we need to go in, evaluate it, and decide to reject it or not, right? And the reason why we're inefficient is because we're rejecting a lot of points, we're wasting a lot of computational hours, so that's not good. But what you can do, instead of doing rejection and evaluating your likelihood, this is one paper that I really like, and it get really close to, I mean, it kind of successful, but they're still not adopted by the community. Then there's a reason for that, which is the next slide. But what they did here is give me the data. Okay, so I train my neural network to look at a collection of time series, right? And I learn this transform to map a Gaussian to whatever gravitational wave parameters. So in training, they just look at a bunch of time series. Okay, a lot of synthetic data, and because it's a training, so you know the true theta, right? And you look at a large collection of time series, then you learn how the probability distribution look like conditional on data. And the flow chart here just to show that in reality, you take the strain data, make it an embedding, you know, plug it into the flow, and then because you have already learned this function, now if you give me the data, what I can do is I sample the Gaussian, conditional on the data, and I just generate actual samples of my target. I don't need to reject. There's no rejection going on there. It's just generating the final distribution. That's the idea of that paper. I'm not going to show any result of that, but this comes with some skepticism. Just to be clear, I really like this paper, although it comes with these laundry list of like problem. So there's a couple of things. So like first off, they start with a large bank of training models. If someone goes in and tweaks the model a little bit, they're retrained, right? Wait for another 2 weeks, and a new model comes out, and you can redeploy the model. Not the most ideal case, but it's okay, right? The next things that you need to be very careful about is this is another paper from another guy that showed what's the distribution of a model actually looks like. So these are numerical models that people have, and they're not uniform, right? So if you train a neural network algorithm or the normalizing flow on this distribution of point, you're going to have better performance, you know, here over like here, because if you have a new point somewhere around here, because you haven't seen example like that, you can expect that the network don't know what it's doing, and you have more error. So you need to be very, very careful about your data balance, you know, or like whether you're missing data in some region, how they're uniform or not. So that's another problem. And the third problem is kind of like a more serious problem is you train, right? Like you validate on a specific set of data that you have. But the real data is never guaranteed to have exactly the same properties of your training data. How do you assess the convergence of these new data when you're not guaranteed, like, right? Like if you have a point here, how do you make sure that there's some notions of convergence or deviation from convergence that you can look at? That's something that's unclear. And these two are rather minor problem, but they're a longer signal, they're a shorter signal. One is harder to train, but that's okay, right? Give them a couple more graduate student, a couple more years, things will be solved. And, you know, they still take orders of like 100 CPU hours, much better than a couple 100,000, but, you know, still not ideal and all that. So people try pure machine learning based method. Again, I love this paper, you know, only good thing to say about this, but they do receive some skepticism. Retraining, data balancing, notions of convergence, you know, not ideal. Now, this is now, instead of using normalizing flow to just generate a target, so this is something that we're done. So typically when we run MCMC, so consider the following example. So if you have like a bimodal distribution, if you run MCMC on them, like, and you have multiple chain, they will kind of like render around their own mode and all that, right? And they never talk to each other. So if you look at convergence of this, because this particular MCMC chain have not explored that one, you don't know the normalization between the two. This MCMC chain will tell you, oh, this is how the distribution look like, only on the right part, and the left one will tell you only about the left part, but you don't know the normalization. You have to figure that out. So that's why, you know, MCMC usually have a stroke when they have multimodality or like non-local geometry. One thing that we do is we combine MCMC with normalizing flow, but not in the way of traditional MCMC does. Neither do we use normalizing flow to learn the data directly. But what we did is, as we have these two MCMC chain walking around, exploring their local landscape, we also train a normalizing flow globally to look at the global landscape. So the underlying here is not the target, but it is the normalizing flow proposal. And we use that to propose jump, okay? So instead of using a normal, like the critical bit here is instead of using a normalizing flow to directly generate the data, we're only using it as a proposal. We're only using it to help the traditional MCMC, which, right, like the reason why MCMC is inefficient because it's proposing jump in region that it's not, except like, highly probable. But if you use a normalizing flow to learn the global landscape and use that as a proposal, you can learn to be efficient. This is the key, right? Like you combine normalizing flow and Monte Carlo together, you can have, at the core, because normalizing flow is only a proposal here, this is effectively still an MCMC algorithm. So you can have all the convergence tests. It works as well as an convergence test, you can test it. Perhaps the same, like if your MCMC is well behaved, you can still believe that after you run it for a million years, it will give you the correct answer, that sort of properties. But it solves the inefficiency problem. Okay. And so this is just to showcase what kind of posterior they're talking about. So this is one of the gravitational wave inference problems that we're trying to solve. Don't worry about the axis, but here is the 11 dimension. So the full problem is 15 dimension, but we can work on some smaller dimension version of that. And this is just cascade, but this is 11 dimension sampling problem for a particular gravitational wave event that we've seen. This is actually the first event. Okay. And you can see a lot of all these are different parameters of the gravitational wave. This is mass, spins, and distance, and sky angle, and so on and so on. Okay, good. And you can see there's highly non-trivial geometry in this space, right? Multimodality like here, which will definitely give normal MCMC a stroke like this. Well, this one not necessary, but these banana shaped things, you have done MCMC, this is not going to fly. And but our algorithm, combining normalizing flow with MCMC, you can get this. We get this in 5 minutes on a decent GPU. It's better, beating the normal MCMC. It's beating the normalizing flow machine that people build. There's a lot of engineering going into this, but yeah, by combining MCMC, my bottom line here is by combining normalizing flow and MCMC, we can actually get something that is pretty powerful. This is Ed. Call me if you're interested in black box interface, very user. If you have MCMC problem, try it out. You can pip install it. It's pretty cool. So I'm not gonna harp on this. Second, I'm gonna go a little bit faster because of 10 minutes, right? Good. So that's the first case to show that how hybrid model. You have a part of it is just like a traditional thing, your typical MCMC model, and part of it is enhanced by your deep learning method. And together, this seems to do magic. Okay. The second part is about population study. So now we've seen how let's say you trust Kaze. You solve the problem of solving an inverse problem per gravitational wave event. Now you have 10 to the 6 of them. Solve the inverse problem of 10 to the 6. That's the population study. I give you a catalog of gravitational wave, trying to tell me something about the underlying physics. So this is what we've seen at the very beginning. And if you look at the mass distribution of them, this is how it's going to look like. Again, on the x-axis, the primary mass. So this is the current catalog, how the current catalog looks like. Each of these lines is one event. Each of them is noisy, okay? And there's some pattern here that if you stack them together, the y-axis is normalized to each event themselves. But there's some pattern here, and we want to try to understand what's the pattern underlying telling us. Okay, again, Bayes theorem. Previously, we have our Bayes theorem is just telling us something about the mass and distance and so on and so on. Now you just need to make this hierarchical. This term, like these pi, well, the likelihood is the same. The only new thing is the population model. So what the population model is, given some hyperparameter, lambda, predict the distribution of mass. What would be a good example of population model? I'm going to speed up a little bit and I can take my question later. What is a good, how do people approach the problem? I'll show you example of a population model. This is what people do now. So they look at the data, they draw a line through it. That's it. Easy. Everyone knows how to do that. And by drawing a line, I mean that, they fiddle with different features. I add the Gaussian here, add a Gaussian there, draw a line, power law, stuff like that. And then, so you can imagine the power law spectral index is your hyperparameter, or where the Gaussian lift is your hyperparameter. and they predict a distribution of your theta, which is your gravitational wave source parameters. Okay, and they infer these like different distribution, like power law plus a peak, power law plus 2 peak, and people have been going off this journey a lot. You know, they just strap grad student on it and look at different functional form. Okay, so it's clearly not scalable. Like the problem with this is like how many grad students do we have? We have limited amount of grad students. We cannot just like paralyze like human and make up new functional form. This is not scalable. This is how we're gonna keep writing down new model and model. And also, what does power law plus 2 peak mean? You know, at some point you reach your 15th generation of grad student, they start to put a spline or you know some weird form down. It's like, what do you mean by that, right? There's a problem in that. We're just not scalable. We cannot keep doing it. Now, one thing that we recently trying to do is like instead of writing down a model by human, like let's just use some flexible model to model that. Instead of like, why don't we just use a Gaussian mixture model, right? Oh. So instead of writing it down power law, just use some very highly non-parametric, I mean, very models with a lot of parameters. Like let's say this is a Gaussian mixture. So then you can, like the point here is not to have a model that will exactly, like this is the first step. This is not to tell you exactly what the physics mean or gain insight and so on. This is just to fit the data, okay? To use a Gaussian mixture recently, I have a student that, again, at this point, people should know that I love normalizing flow. This is a work that I have a student work with me over the summer that is recently accepted in Europe. So we basically look at these events and we use a normalizing flow to model the distribution of them. It's basically KDing it, like in short. But yeah, like you form some sort of understanding. Now that's the first step. Okay. Now, like if you have some flexible model that can describe a generic class of data, then you solve the first part of the problem. It's like you don't need infinite series of students. You just need to like find a big enough model, capture all the significance in your data. Okay. The problem is like, what the hell am I looking at? Like, can you tell me like what's the physical meaning of it? Right? I cannot go into the normalizing flow weight and tell you weight 10,000 tells me this physical number. It's not very interpretable. So what we've been doing is like instead of just end with normalizing flow, we do something called symbolic regression. So symbolic regression is a technique that if I give you a series of points and you're trying to find a tree, equation is basically a tree, a graphical tree, and then you can find a tree that like best describes data. So what we did with the gravitational wave example is again, we still have the normalizing flow and the traditional inference machine as the inference part. But now again, we use symbolic regression as a proposal to generate models. So once you have fit the data, you can use symbolic regression to try to generate forms that is a little bit more physical. Like people look at this as like, this is still not physical, what are you talking about? To us, this actually recover in the middle. It actually recover, this is a power law plus peak model. This is a power law plus 2 peak model, and this is overfitting. And we know this is overfitting because we have some measure. So by running symbolic regression, we can actually get equations of that. And we can look at the equation and interpret them and say, oh, is this Gaussian make sense? Does that Gaussian make sense? And stuff like that. Okay. So again, yeah, good, we're on track. So by having this pipeline of traditional inference machine, then pass through normalizing flow, then pass through symbolic regression, when you put them in together, seemingly they can just solve the infinite series of grad student problem, right? Now we have this, right? We don't need to write down new forms anymore. We can just go explore new forms. And the nicest thing here is like, this doesn't have to be an answer, right? Once you have the form, let's say you're not okay with this, like, why should I trust it? You can take this equation, put it back as your model. You can, because now you have an equation, just put it back. Run your typical inference machine, the same thing. What's the difference between me writing down, like look at the data and writing down a form to describe it, then a machine, look at the data, writing down a form to, then running the inference, right? So it's exactly the same. It's just done by the machine. So you can parallel CPU, not HPU. Good. So that's the idea of like using symbolic regression. And but so this is kind of my takeaway slide. I mean, I've shown 2 use cases of how we can different model together, and they kind of like work better and solve some problem. So what I'm trying to bring along in this talk, if you need to remember one thing and one thing only, is the following. So we have inference machine, MCMC, Bayes theorem. We love that guy, and I'm sure people here know more techniques that I don't know. That's not necessarily deep learning based, but instead of throwing that out of the window and replace the whole thing with deep learning, why don't we look at the piece and bulk that is, usually bottleneck? In the first case is the proposal in the MCMC. That seems to be the problem. That seems to be causing the inefficiency. Let's replace that with a normalizing flow and leave the rest the same. Then your diagnostic is good, right? It's the same kind of convergence that you would do. You don't need to come up with a new kind of convergence test. And and in the second case, people were writing down parametric form. They just look at the data. It's like power law makes sense or Gaussian makes sense. So what's the difference between a person coming in and telling you Gaussian or a machine writing down an equation? Because after all, you can still take the equation and go do model selection, go do inference and all that. It's the same thing. So instead of throwing everything we know out of the window, then replace it with machine learning, I will advocate, so let's keep the pipeline, look at it. Okay, this part is heavily bottlenecked either by computer or just human, then we can remove that, replace it by some of the techniques that we have, like either the package will come up or other techniques that have been fine. Then it works better. Now, I gave 3 reasons why we think gravitational wave is kind of hard, and we kind of like solve some of the problem within gravitational wave. These are some of the thought that I have why hybrid methods work better. First is something called we have like put a very strong inductive bias. People have looked at the problem that we looked at for many years. We gather a lot of knowledge and we tailor our algorithm to work well with them, right? We put a lot of knowledge in, and that will make things a lot more efficient. And by throwing that out the window, you basically ask the machine to rediscover everything that people have done. So why do that? Just find the most inefficient part, most uncertain part, replace that with deep learning. And you can keep all the things that is very distilled knowledge in your pipeline. That's good. And the second part is by replacing those parts with machine learning, your model suddenly becomes super flexible. I mean, not super, but it's still very flexible. So we'll have flexibility to deal with very complicated data, very little amount of data, but it's flexible. So if you fix all the deep learning part, right, you just don't train it or something. It's just your normal model. The worst thing that a hybrid model can do is a normal model, and you just let it train. And once you train it, it's gonna become like hopefully if you can train it to be worse, I'm sure you can flip a sign and train it to be better. And finally, the good thing that I really like about hybrid model is because it's the same pipeline, as I said, you can have the same convergence test. If you're running a PDE simulation, it should have the same convergence test that you need to follow through. So the robustness, you don't get a guy like if it is hybrid model, you can just when they come and ask you, oh, how do you know your pipeline works for this new data? Then you go back to the traditional school and you tell them, this is how they do it. This is the same thing. This is how I'm going to solve your problem. No new problem introduced by flexible models. So that's the idea. Hybrid model. I mean, there's a lot of technical data that I'll shove under the rug. Happy to take questions.
Great. Thanks so much.